So we just mentioned that the speed of the sound wave propagating in the air is 340 meters per second, but it is at a temperature of 20 Celsius. So I explained to you why the temperature is so important, but now you can try to connect everything together as a whole pictures. So I just mentioned that the propagation of sound wave is actually due to the pressure difference. So you create a pressure difference, but how did you create that? It is due to the compression and rarefaction of the air molecules. So this kind of compression and the rarefaction of the air molecules is related to the motions, the movement of air particles. So apparently, the higher the temperature, the faster the movement of the air particles. So you can expect, even those you don't know the number, when the temperature increase, the faster of the sound wave will propagate in the space. Now let's see how it depends on the temperatures. So if you try to increase the temperature 1 Celsius above the 0 Celsius, the speed of the sound wave will increase by 0.6 meters per second. So this is the order of magnitude, let you know how fast it will be increased. And now let's try to compare these first two first. If you both propagate in the air, so which means the medium is the same, but now the temperature is different. So at the room temperature it is around the 340, but if it is getting warmer and warmer, the wave propagation will be bigger than 340 meters per second. But now if you change the material, the medium, the sound wave propagate, the higher the density of the material, the faster the sound wave will be. So for example, the speed of the sound wave propagating in the water is 4 times faster, and in the steel it is 15 times faster. So here tells you a two important conclusion. So the speed of sound wave is still definitely related to the vibration, oscillation of the pressure and the density. And based on that, the temperature is very important. Also, apparently, the density of the material also plays a crucial role. Now let's take a look about this table, give you a sense of feeling. So if you take a look about the air, material is air at 20 Celsius, and the speed of sound wave is 340. But when the temperature was lower, you can see the speed of sound wave becomes smaller. So this is consistent with what we just mentioned. So the same principle for the water. If it is at 20 Celsius, the speed is 1482. But if you decrease the temperature of the water, the speed of the sound wave will become smaller. So with the same material, when you lower the temperature, the speed of sound wave will be smaller. Now, if you increase the density of the material from the air to the helium and to the water, plastic and copper, you will see the higher the density of the material, the faster of the speed of the sound wave propagate in that material, the bigger and the bigger. So this one basically summarizes the two results we just discovered. So now let's try to ask this question and see whether you have an answer for it. Do sound waves travel faster in the water or in ice? So I have introduced you in the chapter 5 that the density of the ice is actually lower than the density of the water. So you may immediately answer that the sound wave will travel faster in the water than in the ice because the density difference. Yeah? However, the answer is wrong. So the answer is the speed of the sound wave in ice is actually faster. It is 3 times faster in the water. So let's try to study the reason why. So now the water, no matter it is in the liquid water or in ice, they are all made by the H2O molecules. And we just learned that the speed of the sound wave depends on the density. Yeah? So it depends on the material itself. and also it depends on the restoring force. So this is something new and I have not introduced to you, because now the problem is related to the phase transition. So did you notice that when I define the quantity increase, I say it is true only for the process above the 0 Celsius. But if it is involving with the ice, the temperature is below the 0 Celsius now, yeah? So you cannot simply apply the result we just learned. So when you try to compare the speed of the sound wave in the liquid water and in ice, the factors which are important are inertia and the restoring force. And what is the inertia? It is the mass carried intrinsically by the water molecules. Yeah? So no matter it is a liquid water or it is ice, they are all made by H2O. So the inertia is the same for both of them. But they have the so-called different restoring force. What is the restoring force? You can consider is that when you try to push the H2O molecules in the liquid water and in ice, you can consider you try to push them and they will start to vibrate. And the force why they can keep vibrating is due to the restoring force. So the restoring force actually is bigger in ice. So therefore, the speed of the sound wave will be faster in ice because they have the stronger restoring force, try to bring the H2O molecules back and forth. So now this is something new, and please keep in the attention. Now let's have our fourth conceptual quiz today. Now you try to fill your lungs with the helium, not the air anymore. And people definitely see this kind of video. Your sound will sound differently. It won't more like you are speaking like the Donald Duck. So the conclusion you can make is what? About the speed of the sound in the helium. So before you answer that, here it is a hint. The helium at a temperature 0 Celsius, the speed is already faster than air. So the answer is the speed of the sound is greater in the helium. So it is definitely due to the density of the helium is higher and bigger than the air. And you can try to understand the same thing is that apparently when you hear people speaking when they fill the lung with the helium, the pitch is much higher, which means they have higher frequency. What does it mean? If you have higher frequency, because the wavelength is the same, so the speed of the wave will be increased. So this is their way to understand the questions. Now the third example, the wave propagating along a string. So I already shown the pictures, but now let's try to study that. So when the wave propagates along the string, it is a transverse wave. So now, unlike the sound wave, the speed of the wave along the string is determined by two different things. It is determined by the tension of the string, how strongly the string was stressed. And the second thing is the mass of the string. Or you can try to understand is that the density of the string. So these two quantities will determine that how fast the wave will propagate along the string. So the density is very similar to what we just studied in the sound wave. Yeah? For the tension, you can use the concept of the restoring force. So the bigger the restoring force, the faster the wave will be propagated along the string. Now I give you three kind of different examples of the wave. The water wave, the sound wave, and wave along a string. But intrinsically, they are just waves. So they can all be described by the frequency, period, and the wavelengths. Now, let's try to study when the wave, no matter what kind of wave, when they interact with the surface, what will happen? So, if you have a surface which the light or the wave cannot penetrate through, then they will simply be reflected So which means they will change the directions of wave propagations. So now, this kind of reflections, people say there's a law of the reflections. If you have the surface, which is a plane surface, and if you draw a dashed line, and the dashed line is perpendicular to the surface, and this is a so-called normal line. So the normal line is perpendicular to the surface, and this is the direction of wave propagation. And the direction between the wave propagation and the normal line is the theta I. This is the incident angle. Then the law of the reflection tells you the angle of the incident will be equivalent to the angle of the reflections. So the angle of the reflection is that the direction of the wave propagation will be changed. And now the direction of wave propagation of the reflected light or the wave compared with the normal line, the angle is theta reflected. And these two angles, theta I and theta R, are the same. And this is the so-called concept law of the reflection. So this kind of law of reflection everywhere, when you're sitting in the classroom, the reason you can hear when I'm speaking is not simply due to the sound wave propagated directly from my mouth to your ear. It could be also from the reflection due to the ceiling or from the floor. So you will hear my voice from different kind of directions. And this kind of reflections, no matter what kind of surface it is, the reflections will happen. If you are not transparent, then the wave will be reflected. So if you have a very rough surface, then we will say this kind of reflection is a diffuse reflections. If you have a smooth plane surface, then we will say it is a perfect reflections. But no matter what kind of surface it is, the law of the reflections is always respected. But the only difference is now, if the surface is not smooth, you can see now the direction of the reflected wave. The directions are not parallel to each other. They will be in random direction or in many different kind of directions. But if you have a perfect surface, you will find out the direction of the reflected wave are all parallel to each other. But for the diffuse reflection, the direction of the reflected wave is different. They are all in the random directions. So now let's have a final conceptual quiz today. If you try to compare with the dry road, and the scene is difficult when driving at night on a wet road. So why it is that case? Why it is much harder for you to see the road condition when it is raining, and especially at night? So this is not an easy one, but very useful for us, yeah? So the answer is A. So if it is raining, then the road is the wet. So you change basically the property of the surface, yeah? It become much more smooth. So therefore, the reflection is less diffuse. And what will happen? If it is less diffuse reflection, then all the reflection will point to the same directions. And therefore, when you see the road, actually, how did you see that? It is the light from your headlight hit on the road and be reflected to you, yeah? And due to this kind of situation, it is a perfect reflection. So almost 90% of the light was reflected back to your eyes. So therefore, it becomes very bright in the case. And because it's too bright, it makes it harder for you to see and watch and observe the road condition in the case.